We are going to look today into the derivative of trigonometric functions, and we will start with finding the derivative of y equals sine x using first principles. First principle is quite difficult to use. That's why for the next trigonometric functions we will not use any more first principles, but we will find the derivatives using the rules of differentiation learned before, like chain rule for cos x, quotient rule for the others. Then we are going to move on to finding the derivatives of the inverse trigonometric functions, and we are going to find these derivatives by using implicit differentiation. So see how in this lesson the techniques that we learned before about differentiation will be useful in order to find the derivative of all trigonometric functions. Let us remember a useful limit that we proved last time. So we found that limit when x approaches 0, sine x over x is 1. And then related to it, we saw that if I have a composite function, sine of u of x, and the denominator is the same as the argument of the function, converging to 0, then this limit is also 1. Based on this limit, we are going to find another one. So I'd like you to stop this video and think what this limit is using the half-angle formula. I'm going to use a half-angle formula because I want to find this limit using a limit that I already know. So I know a limit relating sinus of x. Yeah. By the way, just by replacing x with 0, I get an undetermination case is 0 over 0, so I need to transform it. The double angle formula for cos x is, and I'm going to use, so we know that it's 2 cos square x over 2 minus 1, but it's also 1 minus 2 sine square x over 2. And I'm going to use this second one because if I put it here instead of cos x, 1 will cancel, and I'm going to be left with sine x, which I know from above. So please do this and then see how are you going to find the limit that you get. Just pause the movie and think for a while. So you hopefully, after replacing cos x within double angle formula, end up with this expression. Now I'm going to try to use the limit about sine that I need. So I need to group a sine x, or sine of an argument of x, with the argument on the denominator to form this limit. So try to rewrite this expression to make it in this form. So I'm going to split my sine square of x over 2 into sine x over 2 and another sine x over 2. But on the denominator, I need an x over 2 accordingly to my result here. So I need an x over 2 here as well. However, I want the limit to be the same because I have an equal sign. So I need to multiply by x squared over 4 that I just divided by here down, x squared over 4. And then from this one I have an over x. So I'm missing that x, which I'm going to put here. So my final limit is going to be, let me write it here again. As you can see, this expression approaches 1. This expression approaches 1 as well. So my limit is going to be minus 2 times 1 times 1 times 0, because x approaches 0, so x over 4 approaches 0. Therefore, my limit is 0. So we prove that limit when x approaches 0, cos x minus 1 over x is 0. I'm going to collect these results on the next page. So here are the important results that I'm going to use. I'm calling this limit 1, limit 2, and limit 3. When I write mathematics, it is very important to label my equations or my important results, and the international convention is on the right hand side of your page, yes, just label them into the brackets so that I can later on refer easier to them. So we're going now to find the derivative with respect to x of sine x using first principles. After each step, pause the movie and try to do the mathematics by yourself. First of all, apply the first principles to y equals sine x. After applying the first principles, I see that I have an undetermination 0 over 0 if I replace h by 0. So if I'm looking at this expression, what can I do is apply the compound angle formula for sine x plus h. So please try. I will get the same undetermination case 0 by 0 because I didn't change anything in the sense of cancelling one of the zeros. But what I've done was that I used a compound angle formula. And now I see that I can group these two expressions together because sine x, when x approaches 0, gives me the 0. So I can group this together and I can group this. I can leave this term by itself because here I can see a sine of h over h, a limit that I recognize. Okay, so let's see what we got. Sine x from these two terms, I factorize the sine x, so I'm left with cos h minus 1. And I split it into two fractions, the expression above. And from this term, I write it cos x times sine h over h. Please notice that x is, in this case, for the limit, is like a constant. Just h approaches 0, so h varies approaching 0. And I can recognize now this limit when h approaches 0 is limit 3 from my previous page, approach 0. And that's limit 1 on my previous page, and this is approaching 1. Therefore, my limit is sine x times 0 plus cos x times 1. Sorry, the derivative. So the derivative of sine x is cos x. We found, therefore, that the derivative with respect to x of sine x is cos x. Let us check with our GDC that the derivative of sine of x is cos x. So if I insert the function y equals sine x, and then I ask my GDC to draw the derivative of cos x. So under the math, I have the derivative, option number 8. The derivative with respect to x, and I don't want to type the function y, therefore I choose it from my variables, y variables, function y1. In this case, it's simple, but sometimes it's not simple to retype it for all x's, yeah. And I want to check that this function y2 is the same as cos x. So I'm typing y equals cos x. I didn't need these two brackets. I need just one set of brackets. The next step is that I don't want to graph the function y equals sine x. I just want to graph these two and see that they overlap. They come one on the top of the other. So that's why I deselected the first one. And now that's my y2 graph, the derivative. And you can see it is cos, y equals cos x. And now when your GDC graphs the second one, yeah, you cannot see it because it's overlapping. How are we going to find out the derivative with respect to x of cos x? I don't want to apply the first principles again, but you can try. It's the same. It's a good practice. I would prefer to find this new knowledge based on the previous knowledge. Now I know how to differentiate sine x, and also we know the chain rule. We have the chain rule, so we know that the derivative with respect to x of sine of u of x is cos of u of x times the derivative of u. So we are going to use this, and I will write cos in terms of sine. So cos x is sine pi over 2 minus x. And now using the chain rule, this is going to be cos of pi over 2 minus x times the derivative with respect to x of pi over 2 minus x, which is minus 1. So we get minus cos pi over 2 minus x, which is minus sine x. So we found that the derivative with respect to x of cos x is minus sine x. Now it's useful to know the trigonometric identities. I use here the two of them, and these ones are sine pi over 2 minus x is cos x, cos pi over 2 minus x is sine x. You can check with your GDC by graphing the derivative of cos x and the function y equals minus sine x that they two overlap. We will keep building to find derivative of other functions, so you can try by yourself to find the derivative of tan x, y equals tan x. Pause the movie and think for a bit. How are you going to find it? It was by writing tan x as sine x over cos x, and by using the quotient rule. How are we going to find the derivative of sec x? Was by writing sec x as 1 over cos x, and by using either the quotient rule, or if you write it cos x to the power of minus 1, by using the chain rule. Same with y equals cosecant x, which you can write as 1 over sine x. Try these three. Your answer should be, for the derivative of tan x, 1 over cos square x, which sometimes also it's written as sec square x, or always can be written like, but then you use a form that you it's more useful. The derivative of sec x is sine x over cos square x. You can use this form as well, and that's the derivative of cosec x. Let's now find the derivative with respect to x of arc sine x. So if I start with writing that actually arc sine x can be written as y, I don't know how to differentiate arc sine x, but I know how to differentiate sine x. Therefore, if I write sine y equals x, I can use implicit differentiation to differentiate both sides with respect to x. So I get the derivative with respect to x of sine y is a derivative with respect to x of x. And now we can pause the movie and try to continue by yourself. So you should get cos y times the derivative with respect to x of y, chain rule, is 1. Therefore, dy by dx is 1 over cos y. We found it, however, it is given in terms of y. I can never differentiate a function with x and give the answer with respect to y, so I need to convert it back to x. So what is cos y in terms of x? I know that sine of y is x. Therefore, sine square y plus cos square y is 1. So cos square y is 1 minus sine square y. Therefore, cos square y is 1 minus x squared. Remember, sine y is x. Therefore, cos y is plus or minus square root of 1 minus x squared. Now I need to make a decision. Is it plus or is it minus? In order to decide, I need to go back and look at my function y equals r sine x. And I know for this function, the domain is between minus 1 and 1. And the range is between minus pi over 2 and pi over 2. Now for this range, when y is between minus pi over 2 and pi over 2, cos y for angles in the first and fourth quadrant is positive. Therefore, I need to take plus. So I conclude that cos y is plus square root of 1 over y squared. Therefore, the derivative with respect to x of arc sine x is 1 over cos y. As the next step, you can try by yourself to find the derivative with respect to x of arc cos x using the same method, and the derivative with respect to x of arc tan x. So use the same implicit differentiation to find these two derivatives. After you have found them, use the GDC to check, and to check both your works, use a formula booklet to see that where you can detect in your formula booklet the derivatives of all these functions.